My name is Charlotte Webb and I am a lecturer in maths education at the Open University.
And good morning from me as well. My name is Uwe Grimm. I'm a professor of mathematics at the Open University. Been there for 20 years.
And today we're going to do a session together about art in mathematics, looking at tilings and patterns. There's a couple of different elements to this. Uwe is going to talk to you about some of the work related to his research, crystals, and then I'm going to do some practical work with you on creating some art based on tessellations. So if you haven't already and you would like to, you can print out a sort of pattern that you can, a template that you can use for the patterns. If you haven't done so already, I've just sent the Google Drive link for you in the chat box. If you've got a printer ready, if you haven't, it's not a problem. You could have a pencil and a pair of compasses. So, you know, the twiddly ones, not the ones you go out orienteering with. Or if you don't have either of those, we're going to use Desmos as an interactive version as a kind of trial today, because this is the first time I've done this type of activity online. So it's quite exciting.
Thanks, Charlotte. So we'll be talking in 3 parts really today. So this is part 1. And it's about, well, the title is Art in Mathematics, Tilings and Patterns, but actually I will be talking quite a bit about nature, because nature is probably one of the best artists there is. So we'll be looking at something that is related to tilings and patterns, and I hope I will make clear how it is related to tilings and patterns, and that is crystals. Charlotte already mentioned that I'm interested in crystals, and the reason I got into tilings and patterns is actually to do with a certain kind of crystals, which I will talk about, I think, in part 3 later on. This is just a nice picture made in some cave in Mexico of some beautiful big crystals. And you can see there's a person down here in the corner. So these crystals are really huge. And they have nice properties. I mean, they look nice, maybe. Well, some of you may have crystals at home, either in jewelry or sitting on a desk somewhere. So crystals have fascinated people, I think, for well, centuries, millennia, probably. This is a very common crystal. You have it in your food most of the time, but this is just slightly bigger salt crystal. And you can see it has a nice shape. In this case, it's like a cube. And this is a different type of crystal, which you can find in winter mainly. It's a snowflake. And you see this has a kind of a regular shape, but it has kind of 6 parts to it rather than 4, as we had in the cube. Here's another nice cube. So not all crystals are transparent. This one looks like it looks like gold. It's actually something called fool's gold or iron sulfide, pyrite. It makes nice crystals again of a cubic shape. This is one that you may have on jewelry. This is emerald, which makes these columns type shapes, which have a hexagonal cross section. And well, what is this? Does anybody know? Well, this is actually a raw diamond. This is the way diamonds look. Well, if you find a nice one, they can be a nice shape as well. This shape is called an octahedron. And weirdly, this is a crystal too. And actually, this is probably more perfect than any of the crystals I've shown before, because this is a man-made crystal. It's made of silicon. And whatever device you are watching us today from, you'll probably have a slice of such a crystal in your sitting in your device, or several slices of such a crystal. It's grown from a melt, and it's grown in a very well controlled way, such that the arrangement in the crystal is as perfect as possible, which is important for the applications in electronics. So these are all crystals. And what is a crystal really? Well, as I mentioned, these crystals tend to have often have nice facets and show some beautiful symmetry. And sometimes they're also nicely transparent and glow in the light and things like that. But what makes a crystal is really the way it is built at the microscopic level. And here is kind of a sketch of a crystal. This could be a salt crystal, for instance. There are 2 different types of little balls here, green ones and gray ones. So these represent 2 different types of atoms. Say the green ones could be chlorine and the dark ones could be sodium. In that case, it would be something like a salt crystal. And these atoms are arranged in a very peculiar way. In this case, you can see they're built on some cubic structure with alternating atoms of each type. And this is what we call a crystal lattice. And so what makes a crystal is the fact that the atoms are arranged in a very peculiar way, which is according to this type of arrangement, which is a lattice. And so what is a lattice? Well, mathematicians like to make things simple. So rather than having a complicated structure like a crystal, which has atoms in it, and maybe they are arranged like this, maybe there's sometimes something missing or something is slightly off the place where you would expect it to be. So for a mathematician, we think of the crystal as a lattice with some decoration on it. And a lattice is it's quite a simple idea. So I start from one point, this is the blue point down here, and I give myself a distance, a length, and a direction. This red arrow tells me the direction is to the right, and this is a certain length. And starting from that point, I just go along that arrow. And if I go one step, I get to this point. If I go another step, I get to that point, and I keep going. And so get a one-dimensional array of points, and this is a one-dimensional lattice. And if I want more dimensions, I just give myself another direction. In this case, I've chosen it to be orthogonal, but it doesn't have to be. It could be skew as well. And I do the same thing. I go along that. This is another one-dimensional lattice. And if I want to have a two-dimensional lattice, I take all points I can reach from my starting point by going a certain number of steps in one direction and a certain number of steps in the other direction. And so I get this lattice, which is not quite a square lattice in this case because my two distances were slightly different. And if I want a three-dimensional lattice like I have in a crystal, I just have to have a third direction, which in this case would point into your screen or out of your screen in some way. And you do the same thing, and you get a list of points in 3 dimensions, which give you the structure that you get in a crystal. So that's one thing. Atoms are arranged in a nice way. And then the other thing that we talked about crystals is that they have a certain symmetry. And symmetry is very important in art. Everywhere you will see a lot of symmetry coming up in the next session. So just wanted to say a few words about what is a symmetry. Well, a symmetry is something that if I have a structure like this lattice and I do something to it and it looks the same afterwards, okay? So for instance, if I take this whole thing and I shift it, the whole picture to the left or to the right, assuming that there are dots going further in all directions here, which I haven't drawn, then the picture will look the same if I shift it by exactly one of these lengths in one of these directions, or 2 steps or 3 steps. It will always look the same. So there is a symmetry in the structure in the sense that I can do something to it, and afterwards I get the same result back. And other symmetries can be about rotating the picture or reflecting the picture, something like that. So we have different types of symmetry. There's symmetry under translation. In this case, what it means is that our structure is what we call periodic, which means it repeats after shifting it for a while. There are rotational symmetries which have to do with rotating the picture. And we say the picture has, or the system has rotational symmetry of order n, say 3, if we rotate by 1 over n of the total angle of 360 degrees. So in the case where we have 120-degree rotation and we get the same picture back, we have a rotational symmetry of order 3. And for instance, the snowflake looked like had rotational symmetry of order 6 because we could rotate it by 60 degrees to get back the same type of picture. And we could have reflection symmetry like mirror symmetry, and there could be other symmetries. For instance, I could interchange different atoms and get back the same structure. So crystal structures based on a lattice can only have certain rotational symmetries. So if we have 2 things, we have this lattice structure, which is periodic in space, and we also want something to be mapped to itself again after rotating it in an angle, you get a constraint. And that constraint gives you only a certain possibilities, and all the possibilities are listed here. So we can only have a symmetry axis of order 1, which means there's no symmetry. So I can only rotate by 360 degrees to get the same thing back. So that's kind of a trivial case. Symmetry axis of order 2, which is 180 degrees. So that is like the lattice I had shown that had a symmetry of order 2. Then there's 3, 4, or 6, but we cannot have anything else. There's, for instance, no lattice that has a in 2 or 3 dimensions, which has a symmetry of order 5. So we cannot have crystals with 5-fold symmetry, or 7, or something like that. And this has also to do with tessellation. So we're coming back to patterns, and Charlotte will talk a bit more about these tessellations in a minute. So here is an example of a tessellation, or of a lattice, if you wish. If you take all the vertices of the corner points, then you get a lattice of the type that I showed before. So this is an example of a tessellation that has 2-fold symmetry. If you put yourself in the center of one of these tiles, doesn't matter whether it's the dark one, the reddish one, or the brown one. If you put yourself in the center and rotate 180 degrees, you get the same picture back. There is a 4-fold symmetry case here as well, in which case I have squares. Again, if I put myself in the center of any of these squares, I rotate by 90 degrees or multiple of 90 degrees, I get the same picture back. And here's an example for 6-fold symmetry, which you can find in nature as well, in honeycomb. So if you put yourself in the center of the hexagon, you see that if you rotate by 60 degrees, this hexagon moves to this one, and this moves to this one, and so on, and the structure looks the same. So these ones exist. But if you try to do something with pentagons, it doesn't work, because if you take regular pentagons and you put them next to each other, they unfortunately don't fit together like this, because the angles don't add up to 360 degrees. So in nature, you will find crystals, but if these crystals are built in this way that I was explaining, that they have a periodic lattice structure underneath, the atoms are arranged in that form, then the only symmetries we can find are these symmetries here. And for instance, we have seen cubes as crystals, and cubes have different symmetry directions. So in a cubic lattice, you have a 4-fold direction. If you look along this line and you rotate around this by 90 degrees, you'll find that this corner goes to this corner goes to this corner, and so on. And the same, the cube looks the same. So you have 4-fold symmetry. You have also 2-fold symmetry along this line, which goes to the midpoint of an edge and midpoint of an edge, which is at the back here, which you can't see. So if you rotate about 180 degrees, this corner will end up here, and you get the same structure back. There's maybe a bit surprising, there's also a 3-fold direction, which goes from one corner to the corner that is at the opposite end of the, so it's the long diagonal through the cube. If you rotate around that, you'll see that these 3 corners form a regular triangle, equilateral triangle. So if you rotate, this corner will move to that corner will move to that corner will move to this corner. And so again, you have a 3-fold symmetry. 2, 3, and 4, they are all in the list. So you can have cubic crystals. Mathematicians tell you can have cubic crystals, and indeed they exist. And well, since we are with Platonic solids, these are kind of the nicest Platonic solids, if you wish, the icosahedron and the dodecahedron. And both of these have 2, 3, and also a 5-fold axis. And so this tells you that according to our mathematical analysis, we don't find crystals in nature that have these particular symmetries, because there's a 5-fold symmetry involved here, and 5 is not on the list. It's not compatible with having a lattice structure.
So the second part of this session is said a little bit more about art and mathematics. So we're going to basically take some of the maths that kind of Uwe works on at a higher level with, and we're going to look at a slightly basic version of that maths and kind of what kind of art we can do with it. So this is an example of an Islamic geometry construction that's being painted. We're going to be kind of creating something a bit similar to that as we go through today's session. So first thing I wanted to talk to you about is tessellations. So if you would like to in the chat box, and Uwe can tell me what anybody says. What is a tessellation? Can you tell us what a tessellation is, whether you've heard of it before? Might be something you've seen at school. I come from a teaching background, and this is something that's sort of on and off the curriculum, so you might not have seen it. But what is a tessellation? Any definition or any kind of sense of what it might be?
Can you see it, or?
No, sorry.
I get Escher. I get repetitive design.
Yeah. Excellent.
Is your picture on your wall an example? Is a good question.
Well, yeah. So the picture on my wall is an example of a tessellation. It's quite a complex one. But yes, it is a tessellation. So yes, that's correct. And all these
repeatable patterns, geometric shapes with no overlaps or gaps.
I think we've hit all the points there. So exactly. So repeating, and we're going to be kind of looking at regular and semi-regular tessellations today. So we're going to be looking even more specifically at tessellations with regular polygons. But all of these are examples of tessellations. You can see that these are quite intricate, and some of them have got borders around them and things like that, because these are actually tiles that have been created. And you'll see these in all over the Middle East, parts of Spain, and well, all over the world, really. I'd be fascinated to hear if anybody has been to anywhere like Granada or anywhere in Iran or anywhere like that, when they've seen any of these kinds of tiles, any examples you've seen. There's lots in Spain as well that you can see. So if anybody's seen any patterns like this, or perhaps in your hometown, then do type into the chat box. We're going to be looking at, as I said, quite simple tessellations today. So regular tessellations, basically exactly what you said, no gaps, repeating patterns, but they're based on just using regular polygons. Semi-regular tessellations similarly are made of more than one type of regular polygon, and sometimes known as Archimedean tessellations. And the difference between these and slightly more complicated tessellations is sort of repeating the way that they're arranged. So you can see here, for example, in the top left, you've got octagons and squares, and at every vertex, so every place where they all join up in the corner. So if you take like one of the, if you look at one of the square's right angles, you'll see that it joins up with two octagons. So it's always the square, then two octagons next to each other. It's always the same order. So for example, here you can see you've got hexagon, square, triangle, square, and wherever you go in the tessellation, it's always the same pattern. So it doesn't matter which vertex you go to, it's always got the same pattern. But you can have tessellations which are a bit different. So here's a subtle difference here. We've still got only two such shapes. We've got hexagons and equilateral triangles, but actually the pattern isn't the same at every vertex. So the top right angle that's circled, or corners that are circled, you've got triangle, hexagon, triangle, hexagon. Whereas down here, on the bottom left, you've got hexagon, hexagon, triangle, triangle. So that's known as a demi-regular tessellation. It looks like a semi-regular, but it's just slightly different. It's got a slightly different pattern. So my first challenge to you, which regular polygons can form regular tessellations? So if you just take one of these shapes and you tile them, so there's no gaps, no overlaps, is it possible with all of these shapes? Okay, and if not, then which ones is it not possible with? Even better, can you say why? So think about reasons why some of them will tessellate with no gaps and some of them won't. And if all of that is quite straightforward for you, then have a go at thinking about a semi-regular tessellation. So can you think about which shapes together can form a tessellation with no gaps? So for example, could you put a pentagon with a square, and would they form a perfect? So there should be a link to a Padlet, which just gives you the option of basically recording your ideas on a kind of shared post-it note board, so everybody can see what everybody else writes. If not, you can just type in the chat box and Uwe can feedback to me, and we'll have a look at the Padlet in a moment and see if anybody's put anything on there. It doesn't work in Internet Explorer, is what I've discovered, so you need to open it in something else. But yeah, if you want to add any notes on there, you can say why. You could think about why certain shapes won't tessellate as well as why some will. In the links that Uwe sent you, the second link, and this is something more really that you could do after the session because of time, but there is a link to the website Enrich, which is a really useful website for maths exploration, and they've actually got a little applet where you can click lots of triangles and put them together and see if they fit. So if your head's hurting, I would suggest going on that and having you just picking one shape and seeing whether it tessellates as a really practical way to do it. If I was in person with you in Edinburgh Festival, I would bring a load of shapes and we could have a play with them. But we'll have to do it online this time. And somebody else said 3, 4, and 6. Has anybody else got any agreement with that, or any reasons behind it, perhaps? Let's have a look at the Padlet and see whether anybody's typed anything. Not sure. Oh yeah, lots. Okay. So we've got quadrilateral and short and hexagon. Somebody's put triangle, quadrilateral, hexagon. And we've got some ideas for semi-regular as well. Shapes which do not tessellate pentagon. So what you'll notice is you can actually add a comment onto some of these. So if you have a reason why, then you could type on there. There's lots of common answers here, but no, not quite any reasons yet. Has anybody typed any reasons into the chat box either?
We get, what do we get? Maybe not 5, but I don't know why. Shapes where the total angle eating are 360. I'm not sure. Meeting probably are 360 degrees. 4 won't, somebody says. There is an interesting error in UK street signs for football stadiums. Hexagons do not make a sphere, more of a donut.
That's really interesting. Yeah, I don't know if you heard that, but there's the logo that you see on street signs. You know, like when you see signs for museums or whatever, the sign for a football stadium is basically incorrect because they've made it out of hexagons. Okay. Now, as you've correctly said in the chat box, hexagons do tessellate in 2D. So if I put lots of hexagons next to each other, this 6-sided shape here, they will fit together perfectly. Actually, Uwe showed an example of that earlier, I think, with honeycomb. So, and because of that, obviously, a sign is 2D. So they've used hexagons for the football. But there's a mathematician called Matt Parker, who's a stand-up mathematician, he's called. He actually did a campaign to get the signs changed because mathematically, you couldn't have a football made out of hexagon. It would be flat. You couldn't bend it into a ball shape. So that's why footballs have hexagons and pentagons in them, because they need to be able to curve. They basically need to not tessellate so that they don't make a flat surface, so they can be made into a ball. So that's really interesting. So thanks for sharing that. Somebody said 360 degrees. That is a very good point. So I don't know if anybody else has picked up on that, but if you want angles, if you want shapes to tessellate and have no gaps, the angles need to basically fit together perfectly. It's a bit like a jigsaw puzzle. Thinking about how and why they might fit together perfectly, if we go back to this picture here, we can see here that we've got these 4 shapes fitting together perfectly around these vertex. And we know, as somebody said in the chat box, that angles around a whole point need to add up to 360 degrees. So the reason that some shapes do tessellate and some don't is all to do with multiples. So we know that, for example, a square has 4 90-degree angles. Okay, and if I put 4 squares together, which you probably have seen in tiles in your kitchen and things like that, so you probably recognise that as something that does tessellate, you'll get 4 lots of 90 degrees, and they will therefore fit perfectly. Whereas if you have a pentagon, you'll end up with either too much or too little, depending on how many you put together. I don't want to go through this completely fully because I'd like you to be able to carry on exploring after this session. And as I said, if you go to the Enrich link that we sent you, you can go away and explore not only regular tessellations, but also semi-regular or even demi-regular tessellations. You can also get yourself some physical tiles, either print them out or you can get them online and things if you want to have a proper play and explore. What I would like us to do now is have a go at a maths art activity. You either have, hopefully, a piece of paper, a ruler, a pencil, and a compass. That's the kind of hardcore option. You're going to do it from scratch. Or you have the printout that got sent to you, which is also in the chat box. But if you don't have those, you can join in online. So I've created, it's quite a basic version, but I've got a basic version for you to join in online. If you're using a compass, treat this as a practice run and then have another go later. What you need to do if you've got a ruler and a compass, if you've got Desmos link, you can just go straight away and there's instructions on there. So you can go straight away and have a look. If you have the printout, you're basically just going to skip these first stages and go on to the next pattern. And you could click on the Desmos link if you sort of want to get started, because you'll be able to see what the pattern looks like that you can draw into your template. If you're starting with ruler and compasses, you need to start with your page, your A4 page. I usually start it portrait, so sort of lengthways, and you need to draw a straight line sort of roughly through the middle of your page, a horizontal line. So you can see here there's a horizontal line, blue line here, through the middle of your page. And then you're basically going to build this pattern. Okay, so I'm going to give you a few instructions, but then I would like you to sort of have a go at using your problem solving skills to try and create it. So essentially, the clue is that you start first with one circle. So you start with a horizontal line and a circle approximately in the middle of your page. So your compass point will be approximately in the middle of your page. 7 centimeters works roughly. You could do 5 centimeters on an A4 page. If you draw a circle in the middle of your horizontal line, then you will see where your circle crosses with the horizontal line. Now, if you sort of mark that, you could do it with a felt pen. That's going to be the center of your next two circles. So keep the compass the same width, so either 5 or 7 centimeters, and you draw your next circle on that point. Okay, so you'll end up with 3 circles overlapping. And then you're going to have 4 more points. So 1, 2, 3, 4. Can you see the arrow moving? Yeah. And that's going to be where those circles that you've just drawn have crossed with the first circle. Okay, and then those are going to be your final 4 centers, for your final 4 circles. Okay, so you should end up with 7 circles. Now, again, I suggest that you look at the recording again and perhaps have a go at this later. But if you would like to have a go now, that would be brilliant. And once you have got your grid, or if you're starting from the template, you're going to add in a hexagon using those 6 points, basically, where all the circles cross. You end up with petals. Okay, you can see them sort of, it looks like a flower in the middle here. And around the outside of those petals is going to be your hexagon. And that's going to be the sort of basis for this grid. Now, most Islamic geometry patterns are based on either hexagons or squares, or sometimes also pentagons. But this is a very common starting point, a 6-fold. So we're going to start with hexagon. Then it gets a little bit more tricky. We're going to start adding some stars. So there's actually only 3 sort of steps for this. The first one is the hexagon. The next one is to draw 2 equilateral triangles inside your hexagon, and that will give you a 6-pointed star. If you're in Desmos, you will basically be given this grid, and you'll be given the finished pattern, and your challenge is to work out what's going on. So you've got a little bit more problem solving to do. But essentially, once you've got your grid, you've got your hexagon. You've then got a 6-pointed star inside that, which again is those points that you get from the petals. You've got 2 overlapping triangles. And then the final step, you see this hexagon in the middle that you've just created. You're going to do the same thing. You're going to draw a star inside that. So inside that hexagon, take the 6 points of the hexagon, and those are going to be the 6 points of your. Okay, so the triangle is, if you take, if you've got the hexagon drawn, then you basically take every other point from the hexagon. So see here, there's this point, then you skip 1 and take this point, skip 1 and take this point. Okay, and that's going to give you your equilateral triangle. Okay, so you're using 3 of the points from the hexagon to give you 1 equilateral triangle, and then you take the other 3 points. Now, I find when I'm doing it on paper, I find it really useful to use colors. So I'll color in those 3 vertices, and then I'll join them up. And if you use pencil, then you can do rubbing out when you need to. So I'm going to have a look on Desmos and see what everybody's doing. Oh, lots of lovely stuff. Hopefully you can all see that. So I can see that Dan, Romy, Catherine, Dima, Emily, Catherine, Deborah have all completed the pattern on Desmos. And there's a few more people who are still drawing it. So this is basically what it looks like here. If you're doing it on paper, it's sometimes a little bit slower because you're having to construct it with a ruler, but you should get the same sort of idea. And you'll notice that on Desmos I simplified it slightly. In that on paper, we would continue these lines, these star lines, a little bit further. And that is because when we then tile this hexagon, it makes the pattern a little bit more interesting. So again, if you're somebody who's doing it on Desmos, you might like to have a go later at doing it on paper when you've got a little bit more time. I personally don't like to be rushed with these kinds of things. I like to take my time, have a cup of tea, some nice music, and take my time, color them in. You can get some nice marker pens and kind of make it look really nice. So speaking of which, after this session, if you do have a go at creating this on paper or even on Desmos, we'd love to see your designs. So I have actually created another Padlet for you to share your work. So you could color it in as is. So you could color it in so that you've got all these different sections showing, or you can color it in this final pattern that I've got here, which is basically where you pick out the central 6-pointed star, and then you pick out the 6 hexagons around the outside. And that only works if you do carry on those lines from the star. You'll see this is a very, very common pattern in Islamic geometry. You'll see this on all kinds of palaces and mosaics and paintings. And quite often there's more intricate patterns inside as well. But this is a very common pattern that you can construct. While people are working, I've got some questions for you that you can think about and answer in the chat box. So if we go back to our central grid, as I said, this is a sort of underlying grid for all 6-fold patterns. So all the hexagonal based patterns are based on these 7 circles. So if you have been one of these brave people to do it with a compass, you've actually started, you've opened your doors to lots and lots of patterns that you can create afterwards. So in order to think about which patterns we can create, my question is, I've got this circle here, the central circle which has got the hexagon. I've actually divided it again. So now, as well as my 6 petals, I've got 3 extra lines. So I've divided the circle into 12 sections. So using points on that circle, and there's 12 of them, what different regular shapes do you think we could make? So let's see if anybody can type in the chat box. What type of regular shapes do you think we can make? So remember, regular shapes have to have equal sides. So I think about it as they have to kind of have equal spacing around the circle.
We get quadrilaterals, triangles, and hexagons so far.
Okay, lovely. I think that's a very good start. So you're absolutely right. We could get equilateral triangles if we take points which are equally distanced around the circle, 3 points. We can also get squares. So we are looking particularly at squares here because we're looking at regular quadrilaterals, and we can also get hexagons as we've seen already. So one of the really nice things is we've already seen a 6-pointed star with 2 triangles. But if you have 4 triangles, you can actually get a 12-pointed star.
Yes, and dodecagon has now also been mentioned.
Yeah, lovely. So we could have a dodecagon if we joined up all the points. So that's it. That's perfect. So those are all the regular shapes we could get. And as you can see here, I've made a 12-pointed star out of. So my question is, what other stars could we make? So you've had a clue because you know now all the shapes we can make, the regular shapes we can make. So what other types of stars, 12-pointed stars, could we make? So we've got one which is made up of 4 equilateral triangles. Could we make it in a different way? It would look different to that. The points wouldn't be as steep. They might look different. But what other 12-pointed star could we make?
We get 3 squares and with squares as answers for that.
Okay, perfect. Well, exactly. So I might have given you a bit of a clue there by saying 4 times 3. So 4 triangles is 12 because there's 3 points and there's 4 of them. That makes 12. And the same is in reverse. You could have 3 squares, which would also make 12. You could also have 2 hexagons. It would be a very sort of fat star, but it would be a star. And of course, the dodecagon wouldn't work because you'd only fit 1. So the reason to show you that is just to show you some more patterns, really. So this is another pattern which is based on squares. So you can see here, if you imagine this line joined up, this is made of 2 overlapping squares. And that again comes from the same grid. So that grid that you created with those 7 circles gives you loads of options of different patterns you could make. And one of the things that might be nice if you want to have a play later is to try creating some different 12-pointed stars on paper using that grid. And as I said, there is a printout in the folder, so you don't have to draw that. If you don't have any compass, you can print it out. Or you could just go back on Desmos and have another go because the grid's there and you could freestyle on the grid and draw something different. Most Islamic geometry patterns and a lot of geometrical tessellation patterns are based on these kind of underlying grids. So the one we looked at today was hexagonal. It's actually the same grid as the equilateral triangle grid, because the equilateral triangles, 6 of them, you can see, actually make a hexagon. So if we're looking at regular polygons, there's actually only 2 grids. You've either got this one, which is your triangles and hexagons, and you've got this one, which is your squares. And as I said, there are lots of patterns based on pentagons and other shapes, because you can have combinations of different shapes put together. But these are your common ones, which are used for your regular tessellations. And I've shown you one pattern already, which is this one on the left here. And this is your hexagonal base one. One on the right here is based on a square, so overlapping squares as the basis. And you can see here we've got an 8-pointed star made of 2 squares. That's another very common pattern that you see in tilings and in paintings. The second activity, I did set this up as a kind of home activity, but I'll just run it through so that you can see what you've got to do. And some of you might have sort of gone ahead and done it on Desmos anyway. The second activity is to create this pattern. So it's made of this 8-pointed star and this kind of cross shape. And what the task is for you to make the 8-pointed star. But what's really nice is if everybody makes an 8-pointed star, and if we were in person, we could all stick it on a physical wall. But we're going to do a virtual wall for today because of us being online. If we stick all of our 8-pointed stars together, the gaps that we're left with will give us these crosses, and it will appear like we've got this tessellation. Briefly giving you some instructions which you can go away and do later on, which is either to print out the template, which is in the pack that I sent you, and then to basically take the octagon and create this pattern on the right hand side. Okay, and you've got some instructions, but essentially it's a bit of problem solving. It's a bit of looking at where you think the lines meet and what you think it's made up of, giving you a clue with the 2 overlapping squares as your starting point. And what you will have to do at the end is rub out some bits that you don't need. But again, this is available on Desmos, so you can have a go, and you may have already done so. And then what I would really love you to do is to share your finished piece on Padlet. So you could take a photo, you could scan it in, you could take a screenshot if you've done it on Desmos, and you can stick it up. And it's all anonymous. It's just for us to be able to see all your work. And just finally to say that you can also construct it from scratch without using the octagon template. If anybody's feeling really inspired to get on with their compasses, I've somebody called Semiregular who does lots of tutorials on construction. If you want to have a go, and you can actually create this pattern from scratch.
The patterns we have seen, the regular and semi-regular ones, are all based on a grid structure, which is like the lattice I was talking about in the first part. And now we will be moving to a different part of structures, which is not based on such a lattice structure. And these are called aperiodic tilings. And I'll try to explain what they are. And also, I'll start again with my link to crystals, because actually these do have a link to crystals as well, maybe surprisingly. Okay. In 1982, the world of crystallography was turned upside down by this guy called Dan Shechtman, who discovered something that people thought was impossible, because he found crystals that had 5-fold symmetry or 10-fold symmetry. And as I try to explain, mathematics tells us that these things don't exist. And actually, I think the senior scientist in his laboratory told Dan Shechtman as well that these things don't exist. Look in the standard books, and they don't exist. So something must be wrong. But it turned out Dan was right. And eventually he got the Nobel Prize for chemistry for his discovery, although it took about 30 years to get there. Sometimes these things take a little while. This is a page from his lab book. And what he was doing, he was looking at aluminium manganese alloys. So at the top here you can see Al 25% Mn. So it's some alloy of 2 metals. And this was an alloy that is very rapidly cooled. So you preserve some structure that you see in the liquid by cooling it very rapidly. And then he put it into an electron microscope, and he looked at it in something called SAD. You don't have to know what that means. It's selected area diffraction. But anyway, he looked at it in an electron microscope, and he saw 10-fold symmetry. And you see 10-fold here. And well, it's not quite clear whether these are question or exclamation marks. Look more like question marks to me. But anyway, so he was puzzled by that, and he drew some sketch. And well, classical crystallography tells us such things don't exist, but they were obviously there. So this is a picture from the first publication. So these are these type of pictures you get from the electron microscope, which show you the symmetry. And you can see here some angles. And he was looking at his crystal in different directions. And sometimes he sees this beautiful tenfold structure here. Sometimes it's like a twofold symmetric structure. Sometimes it's a sixfold symmetric structure. And then it's again tenfold. And the angles are exactly matching those that you would expect from the icosahedral symmetry, which I was showing before. So you have threefold, twofold, and fivefold axes in certain directions. And what you see in these pictures is always an even number. So if you have a threefold axis, you always see sixfold symmetry. And if you have a fivefold axis, you always see tenfold symmetry. So this exactly fits icosahedral symmetry, which should not exist in crystals. So that was the big discovery that earned him the Nobel Prize. And these things actually do exist and can be grown. And surprisingly or not, these crystals actually show the symmetry as well. So this is an example of such a quasicrystal, which they are now called, which was grown in Ames laboratory. And you can see it is a pretty perfect dodecagonal shape. And you can also grow them in reasonable size. So there's a cent coin here. Well, it's a few millimeters, but anyway, at least it's not something you only can see in an electron microscope. It actually can grow to microscopic size. So how do the mathematicians explain these structures? Well, it actually happens that mathematicians were there about 10 years earlier with Roger Penrose, who also recently got the Nobel Prize, although for work in very different area on black holes physics. He discovered a tiling, which is now called the Penrose tiling, which is made of two shapes. And there are different versions of it. I'll show a few pictures later. But one way of making it is these two shapes. So it's two rhombuses with 72 and 36 degree angles, which I have to do with 1/10 and 1/5 of the total angle. So you can see where we are heading. We are heading towards fivefold symmetry. If you put 5 of these together, you get a 5-star. So we are looking at these things. Well, if you just have these two shapes, you can still make rather boring tilings. For instance, something like that. Well, it's not that boring, but it still looks like the ones we have seen before. So everything repeats if you move from this point to this point, or from this point to this point. So there's still a two-dimensional grid underlying this structure. So that's not something. From the mathematics, we know that if you have something like that, it cannot have fivefold symmetry. It's just not possible. So this is not the right structure. But if I start imposing restrictions on how I can put these two shapes together, and one way of doing that is drawing these lines and demanding that you can only fit these together if the lines continue across the boundary between two tiles. So for instance, this little circle here has to match either another little circle bit of one of these bigger tiles, or has to fit this circle. So this side could be attached to this side by turning it around, for instance. If I do that, then suddenly you'll find that the structures you can build look like this. And it really constrains it very much. And what you can build always will have fivefold symmetry. Fivefold symmetry in a slightly generalized way, in the sense that you don't necessarily, I mean, this is a very beautiful fivefold symmetric patch, which I've done. But if you go somewhere else in that, I mean, you can continue this. If you go somewhere else, it may not look quite so symmetric. But nevertheless, anything you can find in this tiling, you will always find in all orientations rotated by multiples of 72 degrees, actually multiples of 36 degrees, I guess. So you'll find the same structures in different orientations. And if you had a crystal built of this structure, it would actually look very much like what Dan Shechtman was seeing, because it shows fivefold symmetry in the structure. So this is a model for, well, it's a two-dimensional model, but you can make three-dimensional models as well of these structures, which look a bit similar, just more complicated and much harder to show. And this is difficult enough. So this is a two-dimensional Penrose tiling. It's a lot of fun to try to make puzzles with this. This is a picture from an exhibition where we had actually the possibility to carry these tiles and people could play with them. This is a particularly nice version made of wood. Unfortunately, I don't have them anymore, so my colleague who made them has them. And here is Roger Penrose standing on a version of this tiling. You see these fivefold things here happening here. There's the dark ones are the bigger rhombuses, and the lighter ones here are the thinner rhombuses, and you can see that you get these 5 stars, and you get 5 stars in all kinds of places. Well, but of course that tiling is peculiar in a sense that from the mathematics we know it cannot have a grid underlying it. So it is definitely not a structure that is periodic in a sense that once you've seen part of it, then you can just shift it and it's always the same. It will kind of always look slightly different. So it's quite a mind-boggling thing. It's simple in a sense that it's built of just these 2 shapes, just with that restriction of putting them together, but it actually creates quite a complicated structure. I think there's a PDF on the Google Drive, which you can print out and cut out these shapes and play yourself. So you can try to do these as like a puzzle. So if you see, you can put these tiles together, and as I said, the lines have to continue. So this is one way, just showing you some example. And this so far so good. And well, maybe we put one here, we put one here, we could put one there. Okay, now what fits in this shape? Well, it's a puzzle, but it doesn't guarantee that if you do something that looks fine, it still may be wrong in a sense that you can't continue. And well, does anything fit here? Well, let's try. We can fit this one here. Well, now we are left with a short space here for a small tile, but this line ends here and this line ends there. And if you look at the small tile, all the lines end around this middle point. So we will never get a line here. So no tile will fit in this space, okay? Because the thin rhombus has all the lines sitting around the obtuse angle. So if I put one here, the lines would be here and here, but not here. So this line would kind of stop. So nothing fits. So that tile doesn't go there. Well, can we fit a big tile in? Well, we can't either, because we have 2 red lines here, and they are not on the same side. I mean, for the big tile, the red line crosses here and there. So you can't fit it here, because if it's here, it should be there. So big tile doesn't fit either. None of them fits. So this tile actually was wrong, and we have to take it away again. So maybe we put that tile there, and then you can, well, that one doesn't fit. So you maybe fit that, and so on. So it's a rule that enables you to make a Penrose tiling if you never go wrong, but it doesn't tell you whether you go wrong until you try it. So it's a slightly difficult one to play with, but a lot of fun. And if you manage to do it, you get something that has some nice symmetry. Actually, you can't see the symmetry here yet, but if you continue, you will find that the symmetry reveals itself. So there are different versions of these tilings you can find. This is the same again, just without the decorations on it. So you see there's a 5-fold patch here in the middle, and you get the different rhombuses around. But there are also other versions. There's one that has pentagons. So here you see regular pentagons. So you can tile the plane with regular pentagons if you add in other tiles, like this 5-pointed star. You add in this thin rhombus here and this boat-shaped. This is another version of the same tiling. And it's the same tiling in the sense that if you have this structure, you can actually tell how you replace these 2 shapes by these 4 shapes to get this one, and vice versa. So that's kind of the same structure. And there's yet another version, which is known as the kite and dart. So you have like a kite-shaped thing and a dart-shaped thing. So you see, this is another version, and you can also make a version with triangles and with all kinds of arrow decoration. So there are lots of different versions of the same structure, but they all share the same basic rules. Just it's more complicated. It's no longer a simple lattice made of just kind of 2 directions and equal distances. There's even a final version here, which is not a tiling, but it's a covering where things overlap with a single tile, where you take a decagon with these different colors, and you can put the decagon on top of each other such that the dark areas overlap. It's allowed to overlap on dark areas, and you get the same structure from an overlapping structure rather than a tiling. So there are lots of different ways of doing it. But Penrose's original way, I think originally had started with a pentagon tiling, actually, with this structure. And he was inspired by Kepler, who was trying to make tilings with pentagons. So the final few pictures I want to show are more about the art thing. So these tilings occur in nature, but they're also being used in all kinds of artsy applications. This is actually a tiling that's in front of the Oxford Mathematics Institute. And I think Penrose himself was involved in the choice of the decoration of the tiles by lines, slightly different from the one that I was showing. But you can see that again, the two tiles are here, the slightly darker large rhombuses and the lighter thin rhombuses, and they have some line decoration which continues throughout the picture and creates these beautiful pattern. And it's reflecting. That's why it looks quite nice. This is a building in Melbourne that has a facade which has a bit of Penrose tiles on it. This is a building at Queen Mary University in London. They also have Penrose tilings, and you can also see they have some kind of a rule of how you have big tiles and they are dissected into lots of smaller tiles of the same type, which is also an interesting feature of these tilings. This is one tiling a colleague of mine and me designed once for a novel, and it's in German. I don't think it exists in English. So it's called Quasicrystal, which is the German word for quasicrystals. It has nothing to do with science or with mathematics. In fact, it's about relationship of people. But nevertheless, it's a nice cover. They preferred colors to be a bit more pink, but otherwise it is the Penrose tiling, and you can see it has been colored. The tiles have been colored in a way to highlight certain kind of features, like these continuous lines that go through the whole tiling at different sizes. And this is a more artsy version of the Penrose tiling, which a colleague took this picture. I think it's in a museum in Mexico somewhere, but unfortunately I have not been there, so I have not visited that one myself. And that's really the final picture. Maybe I should just try to answer was it Brendan's questions about which things appear in nature and which things don't. So nature is very good at making these things. It can even make these very weird tilings. There is a lot of discussion still on how nature does it, because as I said, if you do it like a puzzle and you put things on, you can't be sure that it's the right thing you do. You may have to try, and then at a later stage you realize, oh, nothing fits anymore, so something was wrong, and you go back. And nature, of course, if it grows a crystal, doesn't really quite do that. So nature will just find ways. It will try to grow a structure that is optimal in some sense, the minimum energy thing physicists would say. So it finds an optimal structure, but sometimes if it has grown something and it isn't quite optimal, it doesn't necessarily go back. It will just keep going and make a little mistake. And no crystal is really perfect as the mathematics. Even a perfect diamond has places in it where the atoms aren't quite in the right place and things are moved a bit. So nature will just ignore that and will still grow these structures. Are there structures that don't exist? Well, we have found these quasicrystals now with 8-fold symmetry, 10-fold symmetry, and 12-fold symmetry. Nobody has found any with 7-fold symmetry or with 13-fold symmetry or something like that. So there seem to be good reasons why that doesn't exist. But as always, it is dangerous to say things don't exist. It's always possible that somebody will find them eventually. But it looks like 8, 10, and 12-fold symmetries are of these non-periodic structures are the ones that are realized in nature. And maybe to finish that, these things were discovered in the laboratory, and people were thinking of, do they exist in nature in the sense that they actually form by themselves in nature? For a long time, we thought that was unlikely because most of the structures in terms of the crystals contain a lot of, but they are metallic alloys containing elements like aluminium and zinc, which don't appear on Earth in metallic form just because there's too much oxygen around. And so any aluminium would be in an oxide version. However, people have actually found them in some strange minerals that were dug up in Kamchatka in Russia ages ago, and which are believed to be formed by meteorite impact. So in space where there's no oxygen, you can have metals, and so they can form under these circumstances. But on Earth, they're probably not very likely to form.
But otherwise, thank you very, very much for coming along. It's been really nice to hear from you in the chat box, and to see your work on Desmos as well.
Okay, well, thank you all very much for joining us today, and hope you enjoyed that and got some interesting ideas. And if you walk around in different places, once we can travel again, you may keep an eye out whether you see some of these weird patterns. So, for instance, in Helsinki, the whole pedestrian zone is covered in Penrose tilings, which I noticed when I visited there some years back, which is quite surprising. I don't think there's any direct link between them. Somebody just thought it looks nice, I guess. So there's some interesting things to discover.
Exactly. Yeah, you'll find yourself now. As soon as you learn about them, you'll start spotting them everywhere. So enjoy that. Thanks very much.
Okay, thank you very much, and see you.